Hi students, welcome to the session. I am Dr. K. Varada Rajkumar, Associate Professor, Department of CSC, AIML, MLR Institute of Technology, Hyderabad. In our previous class, we discussed about how to insert an element in AVL tree. In this session, we will learn how to delete a node from AVL tree. So, overview of the presentation. In this session, we see what is AVL tree. So, after that, we see deletion of a node in an AVL tree. So, outcome of this lecture, at the end of this lecture, you all are understand how to delete a node in an AVL tree. So, first we see definition of AVL tree. So, AVL trees are a type of self-balancing binary search tree. In our previous class, we discussed about what is self-balancing binary search tree. So, binary search tree means always the left child is less than or equals to root and the right child is always greater than the root node. Now, so balancing factor means balancing factor of a node k equals to height of left subtree minus height of right subtree. Now, here balancing factor is either 1, 0, minus 1. If the balancing factor is more than 1 or less than minus 1, then we say that the binary search tree is not balanced. Okay. The heights of the left and right subtrees of any node differ by at most 1. So, coming to deletion in AVL tree. So, deletion in AVL tree is same as deletion in binary search tree. The difference is we delete the element from the tree and after that we find the balancing factor for each node present in the tree, and if it is not balanced, then find the condition and apply rotation. So, this is the algorithm we are following to delete an element in AVL tree. So, let us see. So, deletion in an AVL tree involves removing a node while maintaining the balance factor of balancing factor of the tree. Here a general outline of the deletion process. So, these three are the points. So, first, standard binary search tree deletion. The first step is you delete, you follow the same algorithm, so which we follow in binary search tree. So, standard binary search deletion. So, means here we follow the same algorithm which we followed in deletion of binary search tree. So, start by performing a standard binary search tree deletion of the node to be deleted. So, next step is update balance factors. After deletion, update the balance factors of the ancestor nodes of the deleted node. So, next step is rebalance the tree. If after deletion any node violates the AVL property, what is the AVL property? The balancing factor is minus 1, 0 or 1. If the deletion violates this AVL property, then perform rotations to rebalance the tree. Okay. So, let us discuss with examples. When we try to delete an element from AVL tree, we have two cases. So, case 1 is rotation not required. So, case 2 rotation is required. Okay. So, these are the two cases we have. So, let us consider an example. So, consider this tree and delete 40. Now, I try to delete this 40. So, how? So, compare 40 with 70. So, 40 is less than 70. So, traverse to left side. So, 40 is less than 50. So, traverse to left side. So, 40 is greater than 30. so traverse to right side. So 40 is less than 40? No. 40 is greater than 40? No. So the 40 is found here. Okay. So now if you try to delete this 40, where we are going to modify? The address of 40 is stored in 30. Now the right side address, if we make as a null, then this node will be deleted. That's it. Now this is the resultant tree: 70, 50, 30, 60. 30 have only one child, left child. Okay. So this is the first step. So what is the next step? Update the balancing factors. Now what is the balancing factor for 20? What is the balancing factor formula? Height of left subtree minus height of right subtree. For 20 it is 0. For 30 it is 1. For 60 it is 0. For 50 the height of left is 2. Height of right subtree is 1. So 2 minus 1, 1. For 70, 3, 2. 3 minus 2, 1. For 90, 0. For 80, 0. For 100, 0. Now if you observe, all the values are not greater than 1. So it is balanced. It is balanced. After deleting the element 40 also, rotation is not required. Okay. So consider another example. So consider this tree. So now I want to delete 30. Okay. So delete 30 means, so this is the node I want to delete 30. Now, so 30 have one left child. Now, so what is the first step? Apply the standard procedure what we are following in deletion of a node in binary search tree. Now, so 20. Now 30 I want to delete. So 30 less than 70. So traverse to left side. 30 is less than 50. So traverse to left side. 30 less than 30? No. 30 greater than 30? No. So the element found. Now you check that the 30 have any children. Yes, here the 30 have children 20. So the address of 20 is assigned to root of 30. So what is the root of 30? 50. So the address of 20, so let us assume 100. So this 100 is assigned as left child of 50. So this is the resultant tree: 70, 50, 20, 60, 90, 80, 100. Okay. What is the second step? Find the balancing factor. So for 20 balancing factor 0, 60 0, 50 0, 70 0, 80 0, 100 0, 90 0. So all the values are less than 1. So the tree is balanced. So rotation not required. Okay. Another case. Now I want to delete 70. Delete 70. So 70 have 2 children. If you observe, the 70 have 2 children, 50 and 90. So now, so what is the first step? Apply the procedure what we follow in deletion of a node in binary search tree. So 70 is a deleted element. So 70 less than 70, false. 70 greater than 70, false. So element found. Now check the 70 have 1 children or 2 children. Here the 70 have 2 children. So find the successor for 70. So how to find the successor? So already we discussed in our previous classes. To find the successor of 70, traverse to right side. So 70 right side is 90. Now in this subtree find minimum value. What is the minimum value? 80. So now 70 is replaced with 80. So it becomes as 80, 50, 90, 80, 100, 20, 60. So this is the resultant tree. Okay. So now root is replaced with 80 and now delete 80. That's it. Now the final resultant tree is 80, 50, 90, 100, 20, 60. So first step is over. Now again find balancing factor. For 20 it is 0, for 60 0, 50 0, 80 0, 90, 100 0. Okay, now it is balanced. It is balanced. So rotation not required. Okay, this is the case 1. Now we see case 2, that is after deletion maybe the rotation will be required. So consider this example. Here I am trying to delete 60. So delete 60. So 60 is less than 70. Yes, true. So traverse to left side. 50, 60 is less than 60. No, 60 is greater than 50. So traverse to right side. 60 is less than 60. No, 60 is greater than 60. No, that means element found. So now, so 50 right, we have address of 60. Now that become as a null. Now this is the resultant tree. So 70, 50, 30, 20, 90, 80, 85, 100. First step is deletion. What is the second step? Find balancing factor of each node present in the tree. For 20, what is the balancing factor? 0. For 30, 1. For 50, 2. Here we identified AVL property is violated. Then identify the condition. What is the condition? So this is the violated node. In which direction? Left, 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 left. So the rotation is right. Now consider this 50, 30, 20. Right rotation means 30, 50, 20. That's it. So remaining is same 70, 90, 80, 85, 100. That's it. Okay. Here it is L condition and the rotation is right rotation. Right rotation. So let us consider this tree. Here I want to delete node 100. Node 100. So this is the node 100. How we identify? Compare 100 with 70. 100 less than 70? No. 100 greater than 70? Yes. So traverse to right side. 100 less than 90? No. 100 greater than 90? Yes. So traverse to right side. 100 less than 100? No. 100 greater than 100? No. That means node is found. So 100 found. Now if we delete this, we make 90 right child as null. Okay. So deletion is over. Now the second step is update balancing factors. Now for 20 it is 0, for 30 it is 1, for 50 it is 1, for 60 0, for 70 it is 0, for 90 it is 2. So 2 is not allowed. Now the AVL property violated in which direction? Left, right. So left, right condition. So the rotation is also left, right. Okay. So consider 90, 80, 85. So it is the first rotation left. Rotate to left side. 90, 85, 80. Now rotate to right side. So it becomes as 85, 90, 80. Okay. Now this is the final tree. 50, 30, 60, 20, 85, 80, 90. Okay. So this is the final tree after deletion of 100. So let us assume this is the tree. Now I try to delete 30. 30. So how? So 30 less than 70, so traverse to left side. So 30 less than 50, so traverse to left side. So 30 less than 30, no. 30 greater than 30, no. So element found and make the root of 30 left address as null. Okay. Now 30 is deleted. What is the second step? Update balancing factors. Now, so what is the balancing factor of 65? 0. For 60, 1. For 50, 2. It violates AVL tree property in which direction? Right, 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 right condition. So the rotation is left. Okay, so left rotation. Okay, so consider 50, 60, 65, right, right. So the rotation will be left side, left side. So the resultant tree is 60, 50, 65. The final tree is 70, 60, 50, 65, 90, 80, 100, 85. Okay, so this is the resultant tree after deletion of 30. So let us assume, so this is the tree. Now I want to delete 30. So how? So 30 less than 70, so traverse to left side. So 30 less than 50, so traverse to left side. So 30 less than 30, false. 30 greater than 30, false. So the 50 left address will be null. Okay, now 30 is deleted. Now what is the second step? Check the balancing factor. For 55 it is 0, for 60 it is 1, for 50 it is 2. So AVL tree property is violated. So check the condition. Here the condition is right, left, right, left condition. So the rotation is also right, left rotation. Okay, what are the elements? 50, 60, 55. So this is the right, so this is the left. Okay, so the rotation is also right, left side. So if you rotate this, it becomes 50, 55, 60. Then rotate left side. Now it becomes 55, 50, 60. So the resultant tree is 70, 55, 50, 60, 90, 80, 100, 85. That's it. So this is the resultant tree after deleting 30. I hope you all are understand. So how to delete an element from AVL tree. So coming to summary of the session. In this session we will learn the definition of AVL tree. So AVL tree is a self-balancing binary search tree. Here we are balancing the tree with the help of a balancing factor to each node present in the tree. So how to find the balancing factor of a particular node is the height of left subtree minus height of right subtree. So not more than 1. That means the values are maybe minus 1, 0 or 1. If it is more than 1 or less than minus 1, then we say that violates AVL tree property. Here we discussed about deletion in AVL tree, that involves removing a node while maintaining the balancing factor of the tree. Here we follow 3 steps. First step is follow the same procedure in deletion of a node in binary search tree. Okay, second step, update balancing factor of all the nodes present in the tree. If it violates AVL tree property, then apply rotations. That's it. Okay. In next class, we see how to search an element in AVL tree. Thank you.